So my name is Diego. I'm very glad to be here. I've been working for Mellanox for quite some time, and I'm unusually based in Buenos Aires, and I'm on planes all the time, and this was my shortest trip ever. So I'm really glad for the location. I would have preferred to be here in 3 or 4 weeks when the World Cup begins, but this is what it is. I may come back. We'll see. I'm going to be focusing my talk on the underlying infrastructure that makes clusters be clusters, other than the astonishingly increasing compute power that every generation of CPUs provide. There would be no cluster if there wasn't a very efficient interconnect that can create out of a sparse set of high power compute power something that looks like a big, strong machine. And I'm going to focus on the challenges for the underlying interconnect elements that come from the high-performance compute space. But we at Mellanox do business with networks that apply to all spaces where networks are used, and there's a lot of commonality in the problems or challenges that affect general purpose networks for data centers and those that mostly matter to the high performance compute business. So if we look at try to disaggregate the overall problem of an underlying network infrastructure, we'll see that there are a few salient elements in an HPC environment that are relevant in the design for the interconnect. First and foremost, we're looking at clusters with increasing number of CPU cores, with numbers going all the way up to the few millions, all the way up to 10 millions or so. And for that, we need, since we're going to be running on those very strong computers, massively parallel jobs, we will need a way to efficiently scale the communication between these cores, both when it's point-to-point communication and also when it's collectives, which is a much harder challenge. We see today that on every individual node, the number of cores can go all the way to a few hundreds. And for that, when we design our network adapters, we need to do it in a way that takes into account this high number of different threads and processes that could be running on top. It's obviously not an affordable solution to say that the number of NICs that you need to put on each server grows linearly with the number of cores that you populate on the server. So the number of cores per machine has gone up all the way from 1 or 2 back even less than 10 years ago to a few tens these days, and there's still a single network interface adapter serving them all. And these are much stronger cores also at the individual level. There is a trend towards deeper memory hierarchies. The number of caches, and in the storage space also the significant adoption of newer, faster, non-volatile memory technologies such as flash have created a space for a deeper hierarchy, and that also has an impact to the network. The amount of physical memory per core, if we look at a trend, even though the overall amount of RAM per physical node grows, the number of cores per physical node grows faster, so the amount of physical memory per core goes down. And that means that that is also an element that puts stress on the network, because with less local memory, you need more network to move your data across. Functional units, these cores are not necessarily all the same. There have been talks during the previous sessions about the ubiquity of GPUs in modern clusters. That's a trend that we recognize as something that is here to stay. So we understand that the interconnect needs to serve not just a homogeneous type of core. With scale, the failures become a part of day-to-day for everyday's life. With smaller cluster, we could have neglected some of the failures and say, hey, if bad things happen every once in a while, just restart your job. When you grow to tens of thousands of processing cores, you need to assume that during the run something is going to fail, and things need to understandably have a graceful degradation, but you cannot allow your complete cluster to go down in a single failure. And we need to understand that there's a cost associated with moving data. There's power associated with moving data, there's latency associated with moving data, there are bandwidth limitations associated with doing that. So we make our living by creating the underlying infrastructure that allows us to tackle all these challenges into the exascale phase in high-performance computing. Okay, so some of the things that we do have a more hardware-oriented type of solution, and some of them have to do with networking technologies that help write better software or help take advantage of the network through the use of a different software paradigm. Asynchronous communication that is in the process of becoming more mainstream in the scientific compute world through the MPI extensions is, in our opinion, something that is going to allow leveraging the compute resources in a very significant way. It's going to allow much better overlap of compute and data exchange, which, as clusters grow and more data needs to be exchanged, are going to allow better utilization of CPU resources. System noise issues are also related to this. In small, tightly coupled environments, some of these things may have had in the past negligible impact, but as clusters grow, little noise in the impact of operating system scheduling into the compute jobs can be significantly amplified at the end of the day in the performance of the running application. We want to build networks that are very efficient in moving lots of data, but we also want to create networking paradigms that allow data movement to be minimized when possible. So a lot of these things that we're looking at into the future call for efficient computing in the network itself. And one very obvious example for that is aggregation operations, where you need to do a collective operation that calculates the maximum number among tens of thousands of running instances of a job. There's a lot of optimization that can be obtained by doing some of that processing in the network itself. Gilad, in his previous talk about CloudX, was touching on this a little bit, and he was talking about the concept of open everything. And we at Mellanox are strong believers in open standards. We believe that's the way to foster innovation. We believe that's the recipe for guaranteeing that with every generation you will be able to squeeze out of it the most juice. Proprietary technologies have a way to lock into the interests of individual companies, and we at Mellanox have our way of doing things is through open standards. We believe in competing with other technology providers by creating the best solutions where everyone has a fair chance to innovate. We believe that is what fuels innovation in this space, and for that we make use, leverage, and contribute to the development of all these standard technologies that are the key, are at the core of the networks that have been fueling the growth in HPC for the last 10 years. By strictly following standard and open practices, we are in no way saying that we want to block individual companies or people from creating new proposals and test them, promote them before they have become standards. So all our infrastructures, and I'm showing here as an example the way the support, the operating system stack support for the InfiniBand interconnect is laid down, allow for extensions. People can come up with ideas, test them in real life environments, and be part of this community that develops these open platforms, and that we believe is the best way to get the results that are demanded by the following generations of equipment to come. In high performance compute, it's all about speed, isn't it? Every researcher, I was listening to the past two talks, very interesting. We spend most of our time looking at the very basic components that at the end of the day help solve these real science problems. And the most common element that we hear when we go and meet with our customers and maybe the customers of our customers is we need more speed. We need lower latency, we need more bandwidth, we need all of the CPU to be devoted to the number crunching. We don't want any of the CPU to be spent in moving data across. This is what we focus on. We've been working on this since more than 10 years ago, creating technology generation after generation to improve on the performance for starting from the basic benchmarks to show the capabilities of the hardware and the underlying network interconnect all the way up until the application. And we believe we have in place all the elements required for exascale deployments in the not so distant future. ConnectIB is our most recent network interface card. It runs at 100 gigabit per second. It has dual 56 InfiniBand FDR ports and 16x PCI Express host interface. It delivers roughly 140 million messages per second and has a key element for scalability, which is the support for the new dynamically connected transport protocol. This is a real life testing of ConnectIB. Credit to Professor Panda here present on the measurements. We're showing the actual bandwidth of ConnectIB, both unidirectional and bidirectional. If you take it, for example, this is compared with our earlier generation devices. This one here is ConnectX-3. It's the previous generation device. The ConnectIB doubles the unidirectional bandwidth and more than doubles the bidirectional bandwidth when paired with the Ivy Bridge chips from Intel. In some of these cases, the limitation is not from the network interconnect adapter, but most typically from the host interface to memory. But in order to reach and address the challenges, it's not all about raw speed. We can do these chips that are faster, that get better bandwidth, but if we don't look at the overall problem, we don't really get to address all the challenges. And one of the important aspects, I would say there are two main things when it comes to scalability that have a direct impact in the design of the interconnect. One of them, and I'm focusing on high performance computing type of workloads. One of them is the efficiency of collective operations. These are the killer for the network. And the bigger your network is, the more drastic the impact is. So every improvement in the implementation of collective operations has a massive impact to the end result. We're showing here how, through the use of our collective accelerator library, we can get to no impact pretty much on the number of nodes participating in a collective operation. We're showing here an all-reduce and a barrier collective, and we're showing no change in the latency for the completion of the collective through the use of our collective accelerators. Of course, this is just a glimpse on at the top of the iceberg. This is the actual result. There's a lot of networking infrastructure associated with achieving these results. The other aspect, I said there were two aspects. One of them is collective operations. The other one has to do with the amount of context and the times that it takes to set it up in order to create full connectivity on one huge cluster. If you think of it, the number of connection contexts grows as the square of the number of ranks that you have in your job. So as your cluster grows, that number significantly grows to the extent that the amount of memory that you need to devote at each one of your compute nodes for maintaining the reliability context on each one of these connections and the time that it takes to set those up becomes prohibitive. We created for that what I just mentioned. This is called the dynamically connected transport that takes a completely different approach to the managing of this connection context. It creates this context on the fly and on an as-needed basis. So if you think of it, even though a specific process could be potentially talking to every other one process on the network, at any point in time, he's only talking to a number of them limited by its capacity to maintain outstanding dialogues, which is, in other words, a function of the power of the CPU that it's driving it. And the power of each individual core doesn't grow nearly as much as the size of the cluster. So the number of connection contexts that we need out of each node now is completely decoupled from the size of your cluster and only tied to the power of the individual cores running your jobs. In that way, we can significantly reduce, as we will see in this chart, by 3-4 orders of magnitude, the size of the memory footprint required per node to maintain the connection context, and by a similar factor, the time that it takes to set those connections up. In addition to that gain, there's the efficiency by which those contexts are managed that has a direct impact on latency. If you think of it, you're offloading the communication into the NIC. The NIC has limited memory, much smaller than the memory in the host. Having this context be a significantly much lower number makes it such that most of the connections can reside on the on-chip caches, and that has a significant impact to communication latency. This is a run of IMB using the dynamically connected transport for varying message sizes and showing roughly 40% reduction in the latency for the entire job through the use. Just the only difference was the use of DCT instead of the older, more common and prevalent reliable connected. We've had some talks about topologies and those things. I need to keep my talk to 45 minutes, so I will not have time to talk about all the elements that go into account when we design the next generation devices. But there's stuff that has to do with topologies and the things that we do there in order to make it efficient from the end-to-end perspective. There's routers that need to be deployed when your networks grow beyond some size for managing purposes, for isolation, for connectivity. People deploy high-performance clusters that want to have access to some shared cluster where they make their storage. And for that, there's routers. And there's also the related aspect of converged networks. Some people may want to deploy HPC in non-HPC dedicated environments where HPC need to share the fabric and the complete network with other types of traffic. As I was saying, a lot of these things to make sure that the network addresses the challenges for HPC have to do with things that need to be embedded into the network interface adapter that we use for connecting into the network. These network offloads, these things that the network interface card does on behalf of the CPU, instead of spending CPU cycles, become crucial as the need for more and more communication grows. And as we have seen, since need for communication grows with the size of the cluster, the need for efficient offloads grows as well. So we talked about the collective acceleration and how that was so significant to the performance. We've seen how we had completion time for a collective operation stay constant as we were growing the number of participants in that collective operation. This is the hardware beneath that. This is the way this is accelerated. We have hardware mechanisms on the NIC that do some of the compute for the collective operations. These are done on the network. The collective operations are offloaded into the NICs, done on a virtual tree on the network, and the CPU is only bothered when the result is done. This chart shows the impact of offloading an all-to-all collective operation. And not only the impact on the latency for the execution of the collective operation, but also the resulting benefit as you can you continue to use your CPU to continue with your number crunching while the collective operation is being offloaded to the network. One other element that is quite typical of scientific computing environment is how is the network optimized for accessing data, the way data is laid out optimally for compute purposes. And normally a network interface adapter, a very plain network interface adapter would like data that needs to be moved from one node to another to be laid out in a contiguous space, right? That's the easiest thing to do. This, maybe the most basic offload is that network interface adapters read and write their own data from host memory, right? This is the so-called DMA. And the net result of that is that most network technologies, most notably legacy, Ethernet, sorry about that, technologies do a lot of data copying. And it's kind of associated with this, that the application manages its data in whichever way or form its data structures are laid out, but the NIC wants to fetch bytes one after the other from contiguous addresses. This is not very efficient. It's copying data is a big no-no in this space. When you copy data, you're spending CPU cycles doing that. You're traversing your memory bus a lot of times. Ideally, you want the NIC to be able to fetch data from the application data structures and land data into the application data structures on the other end of the wire. We have implemented a set of optimizations for that purpose that allow the NIC to operate in a virtual memory space where each byte could be physically located in a different place, and through smart translation of the addresses, create an illusion of a virtual memory space. So if we look at the end of the day at the packet on the wire, this could be built out of an interleaved 2 columns of a 2-dimensional array, or any other crazy structure that you can think of at the byte granularity level. That's a huge boost in performance for applications because it eliminates the need for data copies. Another thing that it's kind of related to what I just said about memory copies has to do with these smart network interface adapters that want to grab data from user space memory and deliver it across the network. And in order to do that, typically, you need to go through a process in the interface, in the software interface, by which you, from the application, tell the operating system, hey, don't mess with my data because the smart network interface card may be reading directly without you even knowing. That process, typically known as pinning, right? You know, telling the operating system just leave it here, is usually expensive. It's expensive because the act of pinning through the operating system is an expensive thing. There's a lot of accounting that the operating system needs to do, but it's also expensive because the operating system needs to lock that into physical memory, and that kind of bothers its ability to manage the memory and it's using the virtual memory schemes in its most efficient way. We have introduced a concept in our newer network interface cards that's called on-demand paging. Using this scheme, applications don't need to pin their data anymore. All of this is done automatically by the network interface card interfacing with the virtual memory manager in the operating system. So applications can have their crazy data structures with data scattered the way they want it. They can have their NIC access them without having to go and pin them. We, as I was saying before, we understand that in the future to come, there will be an heterogeneous world built with compute power of different sizes and shapes. We recognize today the prevalent x86 architecture. Today it's combined with GPUs. We believe that there will be a moment in the not so distant future where we will see other alternatives, and the networks that we design are optimized for them all. We we take special care in making sure that we're not doing things that are uniquely developed for one type of compute architecture. One of the things that we have done in the not so distant past is we created a technology that it's called GPU Direct. It's an optimization for InfiniBand connected GPUs, whereas originally a GPU would have done its processing by fetching data from system memory, and then the moment it needed to exchange the data would have put it back in system memory to have the network interface fetch it from there. With GPU Direct RDMA, we can have the network interface card interact directly with the GPU memory, and that not only saves latency, but also, to your point, it saves a lot of power, because you get a 3x reduction in the amount of toggling that you're doing on those signals by virtue of accessing the data directly from the GPU attached memory. This is an example of a run of an application taking advantage of GPU Direct. And we can see there where with 96 nodes, there's 100% benefit in terms of latency for the GPU Direct. This is not even considering the other benefits that we just mentioned. Okay, so HPC is all about computing, but storage plays a role. You need to somehow make sure that whatever you calculate is stored somewhere. There's temporary storage and so on. InfiniBand and the technologies, the networking technologies that we do are very well positioned to address the needs there as well. I'm showing here just by way of example some of the more salient benefits of making use of RDMA. RDMA is kind of a perfect fit for the storage world with their big data exchanges. The use of ISER technology with acceleration gives a boost of over 2x in the number of IOPS that you can do as compared to a fiber channel, and with Exascale RDMA, the data access latency is 20x reduced as compared with iSCSI over TCP. Just two examples in this space. In addition to the raw performance benefits of doing storage access using RDMA technologies, our network interface cards also have a way to offload the compute of the data integrity schemes that are typically required by storage technologies. There's something called T10 diff that is basically a CRC computed, data signature on the blocks of data that is computed before you store them, so that if anything goes wrong, that will fail. There will be no silent data corruption, and doing these computations in the host CPU to generate that or the storage targets is very time consuming. Our network interface cards, in this same spirit of offloading stuff that has to do with moving data across, does this automagically. So when data lands into the storage unit, it already comes together with its CRC, its data protection tag. Power. We had a very exciting talk about power. I will just add that creating a power efficient solution goes all the way from the signaling to the software and the management and so on. We take a very careful approach when designing our stuff to make sure that our solutions will be power optimized. The days where power was kind of a third or fourth priority are gone. Scalability presents a very significant challenge in the context of power, and we want to make sure that our solutions can fit within the most constrained power envelopes that are a reality in these very massive and dense data centers. So we have, I will be running out of time if I get into the details, but we have a lot of elements in our technology that allow power reduction and conscious, graceful degradation of performance in order to fit within a power envelope. These big clusters present also the need for very efficient management. We invest a lot on that as well. We take a holistic view at the network, and we have a tool that is called the Unified Fabric Manager that offers state-of-the-art fabric management and monitoring capabilities for the size of clusters that we're discussing in the exascale age. Our InfiniBand technology has been associated with high-performance computing for quite some time, and we take pride in that. We work very hard to make sure that we are the de facto choice when it comes to high-performance networks. And examples of deployments that take advantage of our technology speak for themselves. We are the only providers today of end-to-end solutions in 40 and 56 gigabit per second networks. Our products go all the way from the chips that are used to build the cards and the switches and the software that is used to manage the long-haul solution, cables and modules. We do it all. We believe that in order to succeed in this space, we need to have complete control over the end-to-end solution. People can then choose to mix and match. We show our customers that there's a solution that goes from one end to the other, and we take responsibility on every one of the components that build that solution. Mellanox has recently, maybe I'm not the most appropriate guy to talk about this specifically. Do you want to take that? Who am I to talk about this? Okay.
Well, good afternoon, everybody. People who don't know me, I have been appointed as the Latin America manager for Mellanox. And one of the first steps that we have done here in Brazil is to establish a distribution sales force that would allow us to bring the products at a more reasonable cost. We all know what it takes to bring something from outside from Brazil in terms of taxes, in time, and performance. We are going to increase our operation here in Brazil with pre-sales, post-sales, and professional services. So for the time being, we have appointed Accept as well over 2 distributors that we are going to have here in Brazil with very much focus into the HPC arena. Thank you very much.
And thanks. If there are any questions, I'll be happy to